In the last class, what we learned was about how to predict the output of a system. So if you have an input xt going into a system h and the output of the system is yt, and you want to predict what y of t is going to be, then if you happen to know the output of the system when the input is delta t, so this is denoted by ht, the impulse response. And if the system is LTI, which is to say it is linear and time invariant, then ht really suffices to predict the response to any input. And what we learned was that this is for any given xt, what we learned was that yt is given by the convolution formula. This is in continuous time, and in discrete time y of n is x of n convolved with h of n. And the way these integrals and summations are defined is y of t is integral from minus infinity to infinity x of tau h of t minus tau d tau. So what you're doing is, remember that you're not using x of t here, you're using a dummy variable tau in order to perform the integration, and the output is really dependent on what the variable inside the h of t minus tau t is, right? This is the value at which the output is being evaluated, t. Similarly, in the discrete world, what we saw, and this is the first thing that we saw in last class, you sum over a dummy variable. So here it's k, x of k, h of n minus k. Now the question is, how do you evaluate these things? And we looked at some simple techniques to evaluate this. The one that we focused on was a very straightforward way of evaluating this, which is also very intuitive. So let's take an example to remember that. This example is slightly different from the one we took in the class. Let's say our x of n is 1 at time 0, and at time 1 it's minus 1. And your h of n is 1 at time 0, half at time 1, and 1/4 at time 2. Okay, and I want to compute the convolution, so I want to compute the output of the system when xn is put in as input to the system with this impulse response. So yn is, as we said, summation k equals minus infinity to infinity x of k h of n minus k, right? Now if you look at x of k, it only takes non-zero values at 0 and 1, so this is just x of 0 times k equals 0, this is just h of n, plus, again going back here, x of 1 times h of n minus 1. Right. And so what really is going on here is that we are taking the first impulse and replacing the impulse response with it. So you get a 1, half, 1/4, and you take the -1 and you add and you replace the impulse response with it, so you get a -1, -half, 1/4, appropriately shifted, that is shifted by 1, right? If you want to plot this, this is equal to a summation of two signals. X of 0 is just 1, x of 1 is -1, so you get 1 times h of n, which is 1, half, and 1/4, and you add to it another signal which is shifted by 1, so h of n -1, right? And it's -1, -half, -1/4. Right. And if you add these two, then you get the output, which is 1 at 0, then -half at 1, -1/4 at 2, and another -1/4 at 3. So simple enough, right? And now I want to show another way of evaluating this summation, which is called the flip and drag method. The flip and drag method is really only useful or is most useful when you're talking about continuous time convolutions. So you have continuous time systems and you want to predict the output. But it's slightly easier to illustrate it in discrete time. So I'll first illustrate it in discrete time, and then we'll look at some evaluations in continuous time. Okay. So let's look at flip and drag method. So this method is really always applicable. It tends to be slightly confusing, just as a word of warning. It's not as intuitive, but if you follow the mathematics of convolution, it's really coming from the mathematics, and if you follow the mathematics, then the method makes a lot of sense. So what's so to say the algorithm, the method? So what you do is you first plot x of k versus k. Remember, k is the dummy variable over which we'll be summing. And then starting with n large and negative, you plot h of n minus k versus k. Now remember, the interesting aspect here is that you're plotting h of n minus k versus k. So what this really is h of minus k plus some, think of this as a constant, minus k plus n. If it helps replace n by an n0, conceptually that can be somewhat easier to deal with in order to remind yourself which is the variable that you are varying. Yeah. So how do you compute this quantity? Remember from our elementary signal transformations that what you can do is you first shift by n, and so first shift h of k by n and then reflect it about the y-axis. And remember, when you're shifting by n, if n is less than 0, that corresponds to a right shift, a delay. N is greater than 0, it corresponds to a left shift. Okay, so the final step is, and this is just something to remember, that for this n, you compute y of n, which is as before the summation xk h of n minus k. But the advantage is, now that you have plots for x of k and h of n minus k, you can graphically multiply these and you can compute this summation. Now just remember that this summation is to be computed for every value of n. So for each value of n, you compute this infinite summation, then make it, let's say for n equals 3, you compute this infinite summation, then for n equals 4, you compute this infinite summation, and so on, right? And this has to be done for every convolution that you do for all values of n, right? So once you do this, then increase n by 1 and go to step 2. Go back up here. Okay, so easy enough, right? But what happens is that this flipping of h of, so sort of drawing h of n versus k, which flips h of n minus k, is actually a useful intuitive technique to understand what the convolutions will look like in the continuous time domain, more so in the discrete time domain. Let's quickly look at the same example again. So you have an x of n, which is given by 1 minus 1 at 0 and 1. And h of n is taking values 1, half, and a quarter at 0, 1, and 2. Okay, and both of these signals are 0 otherwise. So we want to compute the convolution, so let's compute x of k. Well, that's just x of n, replace n by k. Let's compute h of n minus k. It starts at, going in the reverse direction, it starts at k equals n is the first non-zero value, which is 1, which is h of 0. And then at n minus 1, its value is half, n minus 2, the value is 1 quarter. So now what you can do is, let's take n equals 1. Okay, so, or let's, if you want, let's take n equals minus 1. So for n equals minus 1, right, if you plot your signal h of n minus k, so it's minus 1, so it's h of 1 minus k, right? H of 1 minus k starts at n equals n equals minus 1, it's h of minus 1 minus k. So you start at minus 1 and you get 1 and then a half and then a quarter, right? So it's minus 2, minus 3. Now if you multiply these two signals, right, there is at no value x of k and h of minus 1 minus k. If you take a product of these two signals, at no value of k is the product non-zero. So clearly y of minus 1, which is equal to the summation of the product. So you take product of x of k, h of minus 1 minus k, right? And this product is 0 for all k, which means that y of minus 1 is also 0. Now if you compute y of 1, right, so now the signal shifts 1 to the right. So to compute y of 1, right, what do you do? Or let's say y of 0 first. So to compute y of 0, you get h of minus k. What does h of minus k look like? It's just the signal shifted by 1, so you get a 1 here, a minus half here, and a minus 1 over 4 here. Okay, and again this is versus k. So if you compute y of 0, it's take a product of h of minus k and xk. So when you take a product, you get a 1 at 0. So you'll get, but at no other value will get, no other value of k will you get a non-zero value. So y of 0 is just 1, right? Take essentially a product of these two and sum the product of overall values of k, right? And similarly, if you plot this, you'll get y of 1 is minus half, and I really encourage you to check these. Y of 2 equals minus 1 over 4, and y of 3 again equals minus 1 over 4. So the same answers as before. Now the interesting part really shows up when you start doing convolution integrals using this technique, because it gives you a lot more intuition into what values are non-zero and how to compute them. So let's take an example to understand that. So in this case, what you will do is that you want to compute y of t, which is a convolution, a continuous time convolution of x of t and h of t. What is that? That is integral from minus infinity to infinity, x of a dummy variable tau, h of t minus tau d tau. So what you do in this case is very similar to the discrete time case. You plot x of tau versus tau, and then plot h of t minus tau, preferably starting with large and negative values of t. Again, you plot this versus tau, and remember this is the same as h of minus tau plus t, right? So it's really a function, it's really varying with tau. T is something fixed. And then at this value of t, you evaluate the integral, and the plots make it clear at what values of t this integral is non-zero. So integrated x of tau h of t minus tau d tau, right? Now remember, this is the flip and drag method, right? You can compute the convolution just by straightforward integration, but this once you get used to it, this is a quick way of understanding what the convolution is going to look like, and to be able to figure out where the non-zero values of the convolution will be. So let's take an example to understand this. And the example I'm going to take is my x of t is u of t minus 2, and my h of t is e to the power minus t times ut. Okay, so really x of t is just a step function, but doesn't start at 0, it starts at 2. And h of t is a decaying signal which starts at 0, right? And the peak value for both is 1. Okay. So my question is, how do we compute the convolution? Well, let's plot them. So the plot is x of tau, and x of tau looks exactly like x of t. So at 2 it goes, and then it has a step function, right? And now let's plot h of t minus tau versus tau. So the value at which the values for which h of t minus tau is non-zero is it starts at t and then it goes in the reverse direction. Right. So from here, now it's clear. You take a product of these two signals, right? And it becomes clear for what values of t this product is going to be non-zero. So I take the product, it's x of tau h of t minus tau, right? I'm plotting the signal that I'm going to integrate over, and what is going on is that, again, this is versus tau. So from tau equals 2 to tau equals t, if 2 is less than t, you get a signal like this, right? And now what is the integration? What is the convolution? Convolution is the integration of this function, right? So my y of t is the integration from minus infinity to infinity of x of tau h of t minus tau d tau, right? So it's clear that this is the area that you want to evaluate. Much like in the discrete time world, there was a summation you wanted to evaluate. So you want to evaluate this integral going from 2 to t, right? So this is simply if you write it down, it's just y of t is but if the value of t is less than 2, right, then it's 0 for t less than 2, because in that case there is no part of the region, no value of tau for which this product is non-zero. But for t greater than or equal to 2, right, you do get something under the curve. So y of t is integral from 2 to t e to the power minus 2 times t minus tau. That's just what h of t minus tau looks like. Integration over what? Over d tau. And if you do this integration, you find that this is equal to half of it actually does require a little bit of algebraic manipulation, but at the end of the day what you end up getting is e to the power minus 2 times t minus 2. And in a way to write this whole y of t, to summarize this nicely, you can write it as y of t is half times 1 minus e to the power minus 2 t minus 2 times u of t, because what this u of t is summarizing is that u of t minus 2, because what this u of t minus 2 is summarizing is that for t greater than or equal to 2 is when you really need to take this function into account. For t less than 2, the value of the function is non-zero. Okay, so that's one example of how to use the flip and drag method to evaluate the convolution in continuous time. There are other examples, and really the power of this becomes obvious when you start looking at rectangular functions. So try this in your free time. So you have x of t, which looks like a rectangular function. So it's 1 here, at time 1 its value is 1, and at time 0 it starts. And you have an h of t, which is identical. So the impulse response is also at time 1, from 0 to 1 it's 1, right? And if you compute the output y of t, what do you think it's going to look like? And the answer is that you flip this quantity h of t to h of t minus tau, and then you sort of bring it from minus infinity. And the way it starts looking at that is that the area starts becoming non-zero when t equals 0. It increases until t equals 1 and then reduces again until t equals 2 and then becomes 0. So do work out this integral, convolution integral, to check that you can derive this triangular function as the convolution of these two rectangular functions. Alright, thank you.